Hi there, I'm Beau Liddell with Images by Beau Liddell. Welcome to my video tutorial on pre-planning Milky Way landscape photos. There's a lot involved with making good Milky Way landscape photos, and appropriate planning will help you better achieve your artistic vision. In this video, I'm going to show you the information and tools that I use to plan these types of star photos. When shooting the Milky Way, I like to include as much of the galactic center as possible, since it's the brightest, most colorful, and most compelling part of the galaxy. And if shooting large multi-image stitched panoramas of the full arc of the Milky Way from horizon to horizon, I need to assess the elevation of the galactic disk overhead, since if it's too high, it won't provide the best result, or may not even be possible to capture depending on the lens I'm using. Now, if you've ever tried making Milky Way landscapes, you've no doubt realized that to ensure that the Milky Way is positioned exactly where and how you want it in a scene requires some pre-shoot planning. You can use planning aids prior to visiting a location with the goal of finding the final composition once you're at the site. Or you can use them after you've developed a compositional vision previously. Perhaps you've already visited the site during the day, and then established in the sky exactly where you want the Milky Way to be. Thereby, you can use the tools to determine if it's even possible to achieve your vision, and if so, when's the best time to go back out and capture it. Of course, these aids can also be used for planning other types of star photos, such as those involving constellations, as shown here with the Big Dipper above an oak savanna during a solar storm. It can be used to plan making star trails, as shown here, or even to help plan making more complicated star photos, such as here involving the Milky Way and the Northern Lights, as captured this past March during the powerful St. Patrick's Day solar storm. There are many tools available these days for planning and timing these types of shots. The ones I'll reference here are simply those that I've used to plan out my Milky Way photos. Of course, you might find or know of other resources or tools on the market or available on the internet that work just as well as the ones I'll discuss, particularly if you're using different operating system platforms or mobile devices than the ones that I use. All of the tools I'll show you are computer-based. But to be fair, good hard copy topographic maps and air photos, when used with hard copy star charts and planispheres, can greatly aid in pre-planning Milky Way landscape photos almost as effectively, especially if you have experience with observing the night sky. However, I found that hard copy tools aren't nearly as convenient and thorough as the computer-based apps that are available today. Indeed, this is a case where the advancement of technology has shined. If you're new to Milky Way landscape photography, initially you'll benefit from an in-depth planning approach, but after developing some familiarity with the night sky, how it changes overnight and through the year, and learn the various aids that are available to you, you'll find that you can really plan out these shots with relative ease. The first thing you need to do when planning to make a Milky Way landscape photo is to find a dark enough location, since even the slightest light pollution can obscure the Milky Way too much. In addition, light pollution drastically influences the color balance of the night sky, as can be seen along the horizon and the right half of this shot. So the less urban light, the better. If there'll be any urban light pollution in the direction I'm viewing the Milky Way, then I'll try to find a spot that's at least 70 miles and preferably more from major cities to get the best results. Unfortunately, there's so much anthropogenic light pollution now around the globe at night that it can be really hard to find a good dark location in some regions. So being able to assess the amount of light pollution in advance at a given location is quite helpful, particularly if I'm unfamiliar with the area. Fortunately, nighttime satellite imagery captured over the past decade by NASA's Earth Observatory make it possible to find good locations to photograph the Milky Way and whether any sites you might already have in mind are likely to be dark enough. I can view this imagery on a couple of free websites, including Night Earth, as shown here, and the Blue Marble website, shown here, looking, of course, very similar to one another. The location map in StarWalk for mobile devices will also show nighttime imagery of Earth, but it only zooms so far, and unfortunately, the imagery isn't very detailed and also doesn't include many navigation aids such as roads, topography, and so forth. So I tend to use Night Earth and Blue Marble the most because those websites provide much more detailed imagery. They operate very quickly if you have a relatively recent computer, and they make it much easier to find locations since they include roads, parks, and other place names, and enable me to overlay daytime air photos and maps, which make it even easier to navigate around. With these tools, I can zoom in and pan to regions I'm interested in exploring, with the darkest areas being the most devoid of light pollution and hence the best for viewing the night sky. If your computer is powerful enough, you can perform tasks very quickly on both of these sites. Both the Night Earth and Blue Marble websites include powerful search engines that will not only find practically any city and town, but also major parks, refuges, large public forest lands, and other landmarks as well, which will improve my ability to quickly assess the overnight darkness of areas I'm interested in exploring. For example, here I'll search the Blue Marble website for Spray Park, Washington, one of my favorite locations within Mount Rainier National Park, and very quickly it finds it. This definitely isn't the type of high performance I'd expect from typical map-based search engines, since such place names often aren't included in location databases. Both of these sites are great, but each has one minor disadvantage over the other. As I've already shown, the Blue Marble site currently has very good baseline map labeling and road functionality with the night satellite mode, and it's far better than the Night Earth site. If I need to access road information to help me navigate around in the Night Earth site, I have to refer to another map to show the roads. However, one aspect of the Night Earth site that I feel is superior to the Blue Marble option, and one that I particularly like, is that Night Earth provides detailed location information for a spot I found in standard degree decimal, latitude, and longitude coordinates, so I can quickly copy and paste it into other site planning apps or paste it to a list of my favorite photo shoot locations. Since producing the original version of this tutorial, I found a couple additional websites that display light pollution data like a weather radar thunderstorm map, namely the Dark Sky Finder and Dark Site Finder websites. I personally don't prefer light pollution data displayed in this way, and the search engines on these sites don't appear to be quite as good as those in the Blue Marble and Night Earth sites, but they're still quite functional. And the Dark Sky Finder does provide some built-in locations with additional information on the specific location, such as whether there's any lodging or camping options, the seasons for best access, and whether there's a fee to access a site that you're just not going to find in the previously mentioned websites. Now, for those who prefer mobile apps, I recently came across an iOS version of the Dark Sky Finder that you can purchase that displays identical information to what you can get on the website. But I'm told it also provides the capability of downloading cloud cover forecasts for the immediate future that might also be useful. Of course, this latter feature won't be functional if you don't have connectivity. It doesn't take much moonlight to influence the color balance of the night sky and obscure the faint light and colors of the Milky Way. So once I've found a dark enough location to shoot from, I need to target the best or darkest days of the month to shoot relative to the moon's phases. To determine the best days lacking moonlight, I can use a variety of apps to find out what day the new moon phase occurs during the month I want to shoot. As you can easily see here, there's 3 to 4 days on either side of the new moon when either too little of the moon will be lit by the sun, or the moon will be below the horizon during the time of night I'll be shooting. Thus, there's a 5 to 7 day window each month when the conditions relative to the moon's phases will be optimal for photographing the Milky Way. Fortunately, there are a number of resources photographers have at our disposal to track the moon's phases, and I've already shown some graphics from Deluxe Moon Pro and Belaclock. But one free internet resource is the Stardate website. Once at this page, all I have to do is select the month and year, and it'll display a calendar view of the moon phase over that month. And at that point, it's pretty obvious when the new moon occurs and what other days I might have good dark skies where moonlight won't obscure the Milky Way. As mentioned, the moon will be below the horizon during the optimal viewing times several days either side of a new moon. I can confirm this by looking up the moonrise and moonset times on the internet or on one of my favorite mobile or desktop computer weather and astronomy apps. So this process establishes in advance the window in days during the month when you should target your efforts to view and photograph the Milky Way. Many astronomy programs and mobile apps provide a handy means of tracking the moon's phases and determining when the new moon will occur each month, and most don't require access to the internet. Most of these apps are available for both iOS and Android mobile devices, and some are also available for Mac OS X and Windows operating systems. The app I happen to use the most on my Macintosh computer to assess my monthly shooting windows relative to the moon phases is Deluxe Moon Pro, which incidentally is a very information-packed program if you're into shooting or observing the moon. And on my iOS devices, I really like to use the planning features in PhotoPills, as well as VelaClock that I showed previously. Once I've established which days of the month I can best view the Milky Way around the new moon, I need to determine when's the best time during the night or nights that I plan on venturing out. This requires an understanding of twilight to restrict shooting the Milky Way during the darkest times of the night. As shown in this graphic, twilight is the glowing light in the night sky that occurs when the sun is below the horizon between sundown and complete darkness in the evening, and between complete darkness in the morning and sunrise. Now, all landscape photographers are very aware of twilight, at least near dawn and dusk, but it's just as important to be aware of the other time of twilight to make the best Milky Way landscapes possible. Twilight is caused by refraction and scattering of the sun's rays in Earth's upper atmosphere that illuminates the lower atmosphere, and is classified into three periods or types of twilight: civil, nautical, and astronomical, as shown here. The length of twilight at a location you might be interested in shooting depends on its latitude, with equatorial and tropical regions experiencing shorter twilights than regions at higher latitudes, and also depends on the time of year, with longer twilights experienced during the summer compared to winter months. So it's important to be able to predict when the darkest times of the night will occur for your shooting location and time of year. Obviously, all other things being equal, the farther below the horizon the sun is, the dimmer the twilight, as shown in this graphic. Civil twilight is the brightest form of twilight, and only the brightest celestial and space objects can be observed at this time. This period of twilight occurs in the morning and evening when the sun is between 0 and 6 degrees below the horizon. Nautical twilight is the next brightest form of twilight, and the term dates back to when sailors used the stars to navigate the seas. During this time, we can easily see the brightest stars, and it occurs in the morning and evening when the sun is between 6 and 12 degrees below the horizon. However, during nautical twilight, there is usually too much atmospheric light to see the faintest night sky objects, including many individual stars. Astronomical twilight is the darkest type of twilight, occurring in the morning and evening when the sun is between 12 and 18 degrees below the horizon, and what I'll spend most of my time talking about. While all the brightest stars are visible, and the Milky Way first becomes visible to the naked eye, as well as to a good camera sensor during this time, there is still significant twilight obscuring the light and color of faint stars, nebulae, and galaxies, including much of the Milky Way. Astronomical twilight also produces a noticeable blue tint to the sky that is difficult to overcome in post-processing. This is important as the brightest parts of the Milky Way contain a lot of interesting color that can't be recovered if you shoot during astronomical twilight. This photo shows a shot taken almost 20 minutes after astronomical twilight dawn in June. I've barely started processing this photo, and I might well give up on it. Normally I want much more contrast, as well as color variation, particularly in the upper parts of the sky and the dust lanes in the Milky Way. But since I was well within twilight, the photo has become rather cool, even after correcting the white balance severely already. And overall the contrast is just a little too low and too monotone from what I prefer, and quite a bit of the subtle dark and light detail in the Milky Way has been lost and won't be recoverable. To get anything more out of this photo, I'll have to spend a lot of time further tweaking the contrast, and it still won't provide as good a result if the shot had been taken just 15 or 20 minutes earlier, or even farther within overnight dark period. What I'm really looking for is something a bit more like this, with richer contrast, color, detail, and a warmer color balance. Notwithstanding cloud cover, moonlight, solar storms, or urban light pollution, once astronomical twilight ends in the evening, the night sky is as dark as it's going to get, although not completely dark due to air glow in the lower atmosphere, as clearly shown by the lighter blue glow between 0 and 12 degrees above the horizon in this photo. But any celestial bodies that are viewable by the naked eye can then be observed. The night sky will then remain dark enough to view the Milky Way and other faint celestial bodies until astronomical twilight begins in the morning. So the period of time overnight between astronomical twilight dusk and dawn is when I restrict shooting my Milky Way landscapes to achieve the very best results. My favorite aids for estimating shooting times relative to twilight are the VelaClock and PhotoPills mobile apps I covered in the previous section. Obviously, there are other astronomy and photography apps that'll provide this information, with the photographer ephemeris among the most popular, but I found these two apps to be among the most convenient for the devices and operating systems I use. VelaClock is available for Mac OS X and iOS mobile devices, and provides both a color-coded graphic of twilight periods reminiscent of the photographer's ephemeris app, as well as a tabular readout of twilight time periods for any saved locations. PhotoPills also provides twilight information in graphic and tabular form, but is only available for mobile devices. I can access twilight data in the app by going to the planning button and scrolling through the information pane until reaching the tabular data. As you can see, like VelaClock and the photographer's ephemeris app, it also has a color-coded graphic on the timeline pane. But unlike VelaClock, I can manually scroll forward or backward through the twilight intervals on the pane. If I have enabled all its functionality, the map will change hue and color as I advance from daylight through the various periods of twilight. When used with some of the other planning aids in PhotoPills that I'll describe next, I find that it's one of the best all-around apps for planning my Milky Way photos. Okay, so at this point, I'm almost ready to go out and shoot the Milky Way at a site. But our home galaxy, and in fact all the stars and celestial objects in the night sky, won't appear in the same location throughout the year due to the Earth's orbit around the Sun, and obviously won't remain in the same location throughout any given night due to the Earth's rotation. Although it's impossible to notice star movement at any given instant, if I cycle through some successive photos taken at a site, or if I were to reference certain stars or constellations relative to landmarks on the horizon over an hour or so, it becomes very apparent that the stars constantly change their position in the sky. Or, to be more correct, we change our position relative to the stars over time. Therefore, to shoot a particular Milky Way landscape with the galactic center where I want it, I must have knowledge of how the night sky changes throughout the year, whether it's even possible to observe the Milky Way in a particular location and time, and if it is possible, be able to predict with some confidence when it will occur where I want it. Fortunately, there are graphic-based planetarium and photography apps that can do this for me. I'll briefly introduce 5 apps that I like to use: StarWalk, SkyGuide, StarChart, Stellarium, and PhotoPills. These apps precisely predict the apparent star movement through time, including that of the Milky Way, and for any given location on Earth, show me the position of objects of interest relative to the horizon, as well as relative to the basic cardinal and intercardinal directions. Armed with this information, I can then scout any particular site during the day with a compass and clinometer, as well as using mapping aids in Studio to predict if the Milky Way will occur roughly where I want it in a scene at any time during the year. After just a little time playing around with these apps, you can develop a very good understanding of how the night sky changes over time. Let's first take a look at StarWalk, which is available for most mobile devices. Frankly, it has a lot of fancy, unnecessary bells and whistles, but it's still a really cool learning resource nevertheless. StarWalk's graphics quality and overall responsiveness is very good, and I love that it can be used without an internet connection. It's quite easy to pan around the sky, zoom in and out, or otherwise orient the view in the direction you'll be viewing the sky at the location of interest. Once I've oriented the view in the proper direction and placed the horizon similar to where I'd place it in the frame of my camera, my favorite feature is that I can easily set up a time lapse by minute, day, or month to quickly assess the approximate elevation, angle, and position of the galactic disk in relation to the horizon and the cardinal directions, and determine how that changes through time. It's also a very handy app for identifying individual constellations, stars, and other celestial objects, and I find it far easier to use for those purposes than referencing a hard copy star chart or planisphere. Since the first version of this tutorial, I've also stumbled across other planetarium-like apps to help plan your Milky Way landscape photos, including SkyGuide for iOS and StarChart for iOS and Android devices. SkyGuide seems to have the best graphics in my opinion, and also makes it very easy to enter custom location information and perform a time lapse. Otherwise, it's on par with StarWalk, although slightly cheaper, which is good news. StarChart will also do the job with very similar functionality and also has excellent graphics in my opinion. So you can't go wrong with either of these two alternatives as relatively cheap apps in lieu of StarWalk. Stellarium is another app I use to predict the location of the Milky Way. It's a very popular app with astronomers as well as many star photographers. And the best part, it's free. It's a Windows and Mac OS operating system program that excels over StarWalk in many capabilities, and I use it for planning shots when I'm sitting at my studio computer. Stellarium is a tremendously powerful visual tool for planning Milky Way landscape photos, but is more involved to use and has a much steeper learning curve. Therefore, I won't provide any more detail on its use in this tutorial. Suffice it to say, should you decide to try it out, the online user's guide will greatly assist you with learning the app. I also discovered that Stellarium is now available for mobile devices and seems very user-friendly compared to the desktop version, and it's quite responsive. While the graphics aren't as good as SkyGuide, they're about as good as StarWalk, and like the desktop version of Stellarium, can display a grid with elevation and azimuth data, which I find quite handy for planning shots, especially if I want to view the information in a visual as opposed to a tabular format. The final app that I've used to predict the location of the Milky Way throughout the year and during any given night, and the app I've used the most over the past couple of years to plan my Milky Way photos, is PhotoPills. This shows the November 2015 version of the app on my iPad. It doesn't have as fancy a graphic interface and ground level views of the night sky as the previous apps I've discussed do, but nevertheless provides all the crucial information I need to plan just about any Milky Way photo. In many respects, I feel it's superior to the previous apps I've discussed, that it works on mobile devices and can function without an internet connection are nice features. Information on ascertaining the Milky Way's position in the night sky is accessed using the same planning button mentioned earlier when discussing estimation of twilight. The second to last table in the info pane provides data on when the galactic center will be visible overnight, along with its azimuth in degrees clockwise from true north, and the elevation above the horizon. These data are quite helpful for planning a Milky Way composition. Elevation data in particular helps me determine if the galactic center might be obscured by topography or whether much of it might be obscured due to atmospheric extinction that occurs within 5 to 7 degrees of the celestial horizon. By tapping the Milky Way button on the left side of the pane, the map displays a thick gray line indicating the direction from the site that the galactic center will first become visible, and displays a dark gray line marking the direction it will disappear. That same display will overlay a radial grid centered on the site, showing the location of the galactic center, which is denoted by the largest white dots and a thick white line, as well as the plane and overhead elevation of the Milky Way relative to the celestial sphere we see overhead. If I advance the timeline pane, the plane of the Milky Way rotates around the grid and the elevation also changes. So these graphics and the associated data give me an excellent assessment of what the sky will look like when on site. The last table in the info pane provides readouts of the azimuth and elevation of both the galactic center and maximum overhead elevation of the Milky Way instantaneously for the site and changes as I shift the timeline forward or back. And you can see that the graphic of the Milky Way button on the left side of the info pane's table also rotates with the timeline, giving another way to visualize the angle of the Milky Way relative to the horizon. The blue indicator bar to the left of the table indicates how visible the Milky Way will be during the darkest hours of the night. More bars represent the darkest nights with little to no moonlight, for example, on or immediately around a new moon. Tapping once on the Milky Way button to the left of the indicator will advance the date to the next new moon, and by tapping twice on the button will advance back to the previous new moon date. Now, if that weren't enough, the Night AR button in PhotoPills, which stands for Augmented Reality, will show you an estimation of the position of the Milky Way as if you were looking at it for the time, date, and location specified. This particular feature will only work on mobile devices that have gyros and compasses built into them. As for me, I rarely use this feature since I have enough experience viewing the night sky, and the other locator features of the app provide all the data I need to assess the location of the Milky Way with confidence. The graphics and tabular data in photopills are very helpful compositionally to assess the angle of the Milky Way as it elevates from the horizon so that I can plan for a shot such as this, and to plan out stitched panoramas of the full arc of our galaxy from horizon to horizon as shown here. So far, the various planning aids have identified a good, dark location, determined the best times to take the photos, and precisely determined where the Milky Way will be when I go out, but none of the apps discussed so far will help me assess the visible skyline at my chosen location. It could well be that on-site terrain or vegetation might obscure the Milky Way from the location I plan on shooting from. Of course, on-site scouting the day before or day of the shoot is always the most surefire approach. But I can't always do that, so it's real nice if I can do a reasonable job assessing the skyline at a site long before venturing out. Fortunately, there's a powerful and well-known application that will let you know whether or not the terrain relative to the true celestial horizon might obscure the heart of the Milky Way at a location. Of course, Google Earth is the software I'm referring to. It's available for Windows and Mac OS operating systems and now for mobile devices as well, but I find it much easier to use on a computer than on any mobile device. Many folks use Google Earth for many different purposes, but I found it to be superb for planning some of my landscapes, including those involving the Milky Way. Google Earth won't address issues associated with vegetation, such as tall trees that might affect the skyline. So for that, I need to scrutinize aerial photos, although the ones that are available from a bird's eye view in the software will give me a reasonably good idea of the type of vegetation I'll encounter if I'm unfamiliar with the site when I zoom in closer to the location. But Google Earth very accurately portrays topography in my experience, even when simulating ground level viewing. Now, if I'm shooting the Milky Way from a location in the upper Midwest, then I really don't need to worry about terrain. But this app is indispensable if I'm doing Milky Way landscapes in areas with a lot of topography, especially in mountain ranges where it's very difficult to assess the skyline, and enables me to scout out potential shooting locations well in advance, thereby maximizing my productivity once I'm on site. As an example, this screenshot of Google Earth shows a view of Mount Rainier from Spray Park in the northwest quadrant of the park. After assessing timelines and location of the Milky Way using other tools, I was able to use Google Earth several months in advance of my trip to hone in on a location that would give me the skyline I wanted compositionally with the volcano in a good location relative to the Milky Way. The only unknown going into the actual shot was the height of the subalpine trees that might have been present on the site that were indicated by the air photo and that were, clearly a potential problem. But here's the resulting shot I got from that exact site in July 2014. As you can see, it did a fairly good job. I would say even a great job, giving me an excellent assessment of what the skyline was going to look like, of course, excepting the trees. I also panned the ground level view in Google Earth past 180 degrees, and combined with information obtained from photopills, was able to confidently plan the capture of this 19-image panorama from the same location. The first time to my knowledge such a shot had been taken or attempted from that part of the national park. Having established the coordinates in advance for the location in Google Earth, I was able to efficiently execute my hiking trip and only had to spend a few minutes to set up the final compositions for these shots so that the vegetation wasn't obscuring the volcano or the Milky Way. As the screenshot in Google Earth showed, the app also has a feature to simulate the night sky, but I generally don't use it too much for that purpose, especially for my Milky Way work, since I found it to be a little less accurate than photopills, Starwalk, or Stellarium. The take-home message, though, is that Google Earth is a terrific aid to assess topography and skylines where all other apps are lacking, and thereby minimizes one more unknown prior to visiting your location. Now, everything is coming together, but one obvious last-minute factor that can still thwart my ability to get a shot of the Milky Way is the overnight weather conditions at my location of interest. Simply put, clouds are bad if I want to view the Milky Way. The last thing I want is risk spending the time, effort, and money to reach a remote location only to be thwarted by the weather. Yes, weather can always turn unexpectedly since forecasts aren't completely accurate. And that was the case when I went to make this panorama, where the forecast predicted clear skies throughout the night and early morning, but instead brought in clouds at the prime viewing time. Fortunately, the clouds were sparse enough for an acceptable result in this case. In general, though, by routinely consulting the weather forecast, unexpected cloud cover has rarely spoiled my Milky Way photo shoots. Therefore, a weather app or weather radio is a crucial tool I use to plan shots of the Milky Way. If I'll have access to the internet, I can get a more detailed 24-hour forecast than if I use a weather radio. And I've used a number of mobile weather apps and websites to assist my planning. By far the best apps are those that provide forecasts at least every few hours, such as the Weather Plus app for mobile devices shown here and which you can get for free. But the single best resource I found, at least for North America, is the National Oceanic and Atmospheric Administration's, or NOAA, National Weather Service website. The site enables me to obtain a spot forecast for the exact site I'll be shooting at, and you can see here that I've brought up a spot forecast for Spray Park in the northwestern quadrant of Mount Rainier National Park. There's a lot of good information in the detailed forecast, and clearly tonight, and for that matter through the end of this week, wouldn't be a good time to consider going out and photographing the Milky Way at this location, even if it were at a time of the month where there wasn't any moonlight. But it's the hourly weather data on this site that I consult most frequently and provides a ton of information useful in keeping up to date with the near-term weather. And if you have mobile weather apps that tie into the NOAA weather system, then they're usually going to be providing periodic information that's drawing right from these hourly weather data. Obviously, the amount of cloud cover is the most important weather variable I'm interested in, but there are also other parameters I find useful. Generally, I want to get a completely clear night, but I might be able to get acceptable results if the sky cover is predicted to be in the 15 to 20% range. Overnight temperatures and winds will tell me what type of clothing I'll need, and relative humidity, dew point, and wind speed will help me assess whether frost or dew formation on my lens might be an issue that I need to contend with, among other things. Fortunately, weather forecasts have become so good compared to several decades ago that usually the short-term 2 to 3 day forecasts are pretty accurate, at least from the standpoint of giving me some confidence of whether or not the night or nights I want to go out will give me acceptable viewing conditions and worth making the trip. All right, that pretty well wraps up the basic steps I go through to pre-plan my Milky Way photos. I hope you found something useful in this tutorial. If you have any questions about what I covered, feel free to send me an email at imagesbybolin@charter.net, add a comment below this video, or you can visit my website at imagesbybolin.com and click on the contacts link. Thanks for watching.